Hey guys, in this video we're going to continue with the example in which we are fine-tuning BERT for toxic comment classification. And I did a bit of more preprocessing because the training process took a bit too long for my liking. And the preprocessing is based on EDA or exploratory data analysis done by this guy right here. So his name is Shishir Kumar. This guy made a very good notebook on the process of toxic comment classification. And the most important thing right here to note is that the dataset contains basically very imbalanced number of categories in which the toxic comments are actually clean. So using this observation and something else here as well, given that the mean text length of each comment is below 128, this basically gives us a way to choose the tokenizer size or the number of tokens that we're going to use when tokenizing the text or the comment text. So using both of those data or data points or this knowledge, I did something a bit different. So if we go again after loading the CSV and looking at it, the first thing that we did was to have a look at the labels or their count for each label, and you can clearly see that the training DF contains a lot less examples if you combine all of this right here. Let me run this again. So the number of all tagged comments, and this is actually quite a bit lower than this number. So we have 151k examples or more in total comments, and only at most, which is of course not the case because we have multi-level classification, only around 33k of the comments don't have this. So one thing we can do right here is to choose all the comments that contain toxic text, and we are going to do that using something like this. So I'm going to basically take all of the rows in the dataset that contains something, some tag, and I'm going to do this based on the row. So you can see a result of this right here. So this will tell us that those 4 comments don't have or are obviously clean, and this is toxic in some way, so it has at least one tag that is not clean. And if we take every example that contains at least one tag, we can say that those are the toxic comments that we have. And now I can see their number right here. So we have only 15k examples, so that's roughly 10 times less than the total examples that we had right here. And similarly, I can get the clean comments. Let me copy this. And if the sum of tags is equal to 0, this will mean that this comment is, of course, clean. And now I can get the shape of both of those. And you can see that we have 36k examples of comments that are clean, and this vastly overpowers everything from here. So one thing that I can do is that I can create a new training data frame. And I'm going to basically take all of the examples that contain toxic comments, and I'm going to get only a sample which will contain 15k examples from the clean comments. So now the ratio between both of those is going to be a bit different. So we'll have roughly the same size of toxic and clean comments. But I want to show you that this will remain the same, and this will be a bit hard to see, but at least we're going to check the first number. So this is a double check for me, at least for me, that I usually do when I am doing some pre-processing, because of course most of the time I get it wrong at the first time. And if you screw up right here in the data processing steps, most of the time your model will produce just gibberish, or it, even worse, might fool you that is performing much better than you expect. So now that we have this information, I'm going to delete the sampling right here. And basically the rest of it is going to be the same. So once again, this is done because the BERT model is taking quite a while to use all of those clean examples. And one thing that you should notice right here is that we are keeping the validation set as clean as possible or unchanged as possible. We are just taking some sample of all of the comments that we have. We don't do any post-processing on it. And this is great because this will keep the original distribution of the comments, and we are going to evaluate our model based on some realistic distribution. So keep in mind that you should maybe keep this distribution as well as original as we are doing right here, no matter what we are doing with the training dataset. So now that this is complete, I'm just going to restart this runtime and run everything. So this will go ahead and redo the pre-processing steps, and this should give us a good starting point to continue with our example. All right, so now that everything has run properly, I'm going to get rid of this, and I'm going to define the number of epochs for which you are going to train or fine-tune the BERT model, and this will be 10. You might try different numbers, of course, and the batch size that we are going to use is going to be 32. So right here, I'm going to pass in the batch size to the toxic comment data module. So this will run the data module, and it will, of course, give us a batch size of 32. So now that this is complete, I'm going to, of course, also get rid of this cell right here. So this is from the demo. And next we are going to enter some modeling information. And so we're going to evaluate the model that we're going to fine-tune using binary cross entropy loss. And basically what this does is a way to tell us how much each of the possible tags and the prediction for it is correct. So given that your model does perfect prediction for each tag, whether it should be placed or not, you should get a number that is zeros or close to zero as possible. So we'll try to, of course, minimize that loss. And the way you can do that is to use BCA loss, or binary cross entropy loss, that is provided from the Torch NN module. And there is quite a extensive explanation of what this does. One thing that you should notice right here is that you need to have targets or labels in our case, and the numbers of those should be between 0 and 1. So this is the first thing that you should notice. And the second thing here is that you can have a look at an example. So this example uses sigmoid and BCA-WOS and basically generates two tensors using some random number generation. And then this one goes through the WOS, and you should notice right here that the input is passed through a sigmoid function. So essentially we are giving the BCA-WOS a probability estimation or probability distribution for each of the possible labels that we have. And at least for me, this wasn't exactly clear. And another thing you should have a look at is BCA with widgets, WOS. So what this does is basically that it combines the sigmoid function with the binary cross entropy WOS. But we are not going to do that right here because we will basically output the result of the sigmoid function as a prediction of our model. So we don't have to apply this after the WOS is computed. So you can try to model this with this widgets WOS, but I think that you should know that this is what it does. Of course, this is not exactly the case because at least in the documentation they state that this version is more numerically stable than using a plain sigmoid followed by a BCA-WOS. So in some cases your training or maybe even prediction, I don't know, might blow up because the numbers that you put in are into the sigmoid and the BCA-WOS might not be good enough or might not be stable. So even though this might be a better way to do it, I've tried with the BCA-WOS and a sigmoid function because it tells me what is happening under the hood. And I think that at least while you're learning, this is a great thing. So what we can do right here is have a look at an example of how BCA-WOS is going to be used. And I'm going to instantiate an instance of the BCA-WOS. And we are going to imagine that we have some prediction from our model. And this is going to be a float tensor. This will be the prediction basically. And I'm going to take some numbers because I don't want to type them in. So let's say that this is the raw prediction in which we are not applying any sigmoid function. Of course, if we apply the sigmoid function, I'm going to show you what the result of that will be in a second. And after that, we have some labels, which are coming, of course, from our dataset. And let's say that the labels have those values. Know that we are using float values here as well, and the numbers are between 0 and 1. Actually, they are only 0 and 1 in our case. So if I apply the sigmoid function over the prediction, you should see that each value now, of course, happens to go between 0 and 1 as well. So this is great. So basically what we are going to do is we are going to pass in the result of the sigmoid application to the prediction with the labels to the BCA-WOS. And to do that, I'm going to just call the WOS. I'm going to pass in the criterion. All right, I'm going to take this. And the targets are going to be the labels, and this will be our output. And you can see that the WOS is a number which is not close to 0 as it might be at the moment. So if I fiddle around with the, let's say, let's say, yeah, this number. If we go over here and do something like this, the loss is lower right now. Next, if I go, let's say, with this number as well, and the loss is lower. So what will happen basically is that the BERT model and our model in general will go to fiddle with those numbers during training, of course, and get them to match the labels by applying a sigmoid on top of that. One thing that the Kaggle competition is going to use for evaluating the performance of your model is going to be the ROC AUC, or the area under the curve below the ROC characteristic. So this will be the receiver operating characteristic. And to understand what this is, there is a very good article on Wikipedia, which I'm going to link in the notebook, and that explains what the ROC curve actually is. But I think that even a better explanation is going to be the machine learning crash course by Google and this scikit-learn page on the same subject as well. But what is a ROC and why we should care about it? Well, ROC is basically going to be a curve which explains how well a binary classifier does. And we are interested in binary classification in this case because we want each tag or each possible tag to have the predicted value as close as possible to the labels that we have. So this will tell us how well each of our labels for each example of which we have, let me go, how well the toxic category or tag is predicted, how well the severe, toxic, obscene, threat, insult, and identity hate. So each of those will be individually evaluated using the ROC curve. And one important thing about the ROC curve is that it is just a plot or a number, or numbers, which are going to be defined using the following. So we have the true positive rate and the false positive rate, which are going to be defined on some curve, which can be plotted, of course. And we have this ROC area under the curve, which is going to be a basic number, which goes from 0 to 1, or most of the time it goes between 0.5 to 1, where a number of 1 is going to be the best possible classifier. And as close as we go to the 0.5, the classifier is as good as a random number generator. So you will want this graph or this chart to go as close as possible to 1. And if you're not familiar with what true positive rate is, for example, this will be the number of true positive predictions, which means that the prediction is true. So if we have an example in which the toxic comment is present into a given text and the model is really predicting this, so we have a true positive right here, and then we will get or add to the true positive the number of false negatives. So what this means is that we have a negative example and our model is unable to get that. Next, we have the false positive rate, and a false positive is something that our model predicts as that it has. Let's say that we have an example in which the toxic tag is not present, but our model predicts it. So this will be an example of false positive. And this should be added in the numerator to the true negative. So this will be anything that, let's say that a toxic is not present in a comment, and our model says that it is not present in a comment. So this will be an example of true negative. If we get those two rates and plot them, you get a curve that is similar to something like this. So basically the area below this chart or this chart right here, is going to be the area under the curve. And this is just a number which goes between, I think, 0 and 1 as well. So you should try to maximize this number. And of course, we are going to use ROC AUC score to do that. And PyTorch Lightning has an implementation for this, so we are going to use it. So this is pretty much how we are going to evaluate our model. We're going to use both BCA WOS, and then we are going to use the ROC score to evaluate how good our model is doing. So now that we have a plan of how we are going to evaluate our model, I'm going to show you a way which you can use to fine-tune BERT or even some other model, in which we are going to use a warning rate scheduler. And for our example, we are going to use something that is pretty standard, I guess, for BERT. We are going to use the linear scheduler with warmup. So we are going to set some number, which is going to be the warning rate. And what this scheduler is going to do is going to go from 0 to the warning rate that we've specified, and is going to do that in the number of warm-up steps that we're going to use as a parameter. And then for the number of training steps, it's going to go from the warning rate, and it's going to go linearly back to 0. So this will be the scheduler that we are going to use. Of course, you can try out some other schedulers, and there is quite a lot of examples right here from the HuggingFace transformers library, which you might want to have a look at. With all of that information in mind, we are going to continue with creating the model itself, and I'm going to do that using a class which we are going to call toxic comment tagger or classifier, however you want to do it. And this will extend from the Lightning module. So this will be an alternative from the PyTorch NN module. And this will be a bit different in a way that we are going to define a training step, validation step, test step, and training epoch end methods, which are not standard for PyTorch training. But let's start with the constructor. And this will take a number of classes, and it's going to take steps per epoch. This will be required for our linear scheduler, and the number of epochs in which we are going to do that, the training itself, which again is going to be required for the linear warm scheduler to warm up. So here I'm going to call the superconstructor, and I'm going to initialize the BERT model, which I've already done. And I'm going to basically take this. All right, I'm going to do save this in an instance of our class. Then I'm going to create the classifier, yeah. So this will serve as a way to get the outputs of the BERT model and convert those into the number of classes which we are going to want to predict. So this as input is going to get the number of the hidden size units into the BERT model. So this will be 760, sorry, 7 BERT base hidden units. Let's check how many those were. 768 hidden units. This will be the number right here. And this will output the number of classes. So I'm going to save the steps per epoch and the number of epochs. And finally, I'm going to initialize the criterion which of course is going to be the one that we discussed, the binary cross entropy was. Next, we're going to define a forward method, which going to get the input IDs, the attention mask, and the labels. This will be a bit strange to you, but we are going to compute the was right here into the forward method. And this is pretty much standard in all of the tutorials that you might see around the net for fine-tuning BERT. And those will be none when you're doing inference, and those will be some value when you're doing training. So you will need to compute the was right here. So I'm going to pass the input IDs and the attention mask to the BERT model. I'm going to run the linear layer on top of the output, but I'm not going to run that on all of the output, but I'm going to use the pulled result from BERT, and I'm going to apply the sigmoid function, just like right with what we did right here. And here I'm going to define the was as 0, and if we have labels, we are going to compute the was itself, just like what we did right here. And I'm going to return the results. I'm going to first return the was, and then I'm going to return the output or the prediction of our model. So next, we are going to define another method, as I've already mentioned. It's going to be the training step. What this can get is the batch and the batch index of our dataset. And from the batch, I'm going to take the input IDs, the attention mask, and the labels. This is basically what a data water returns in this case. And finally the labels. Next, I'm going to pass in all of this through our model, and I'm going to take out the was and the outputs and the model itself. So this will call the forward method for us, pass in the input IDs, the attention mask, and the labels. Okay, so we're almost done with this. Now I'm going to do something that is specific for PyTorch Lightning, and I'm going to output the training was, and I'm going to call the self.walk method. I'm going to pass in the train was, and this will be the was that we are passing in right here. And I want to say that I want to observe this result, and I want to walk it. So when we are actually fitting the model, you're going to see that this value is going to be printed or updated when we are training the model. And the result of all of this is going to be a dictionary, which will contain the was, the predictions, which is going to be the outputs, and the labels. And you'll see why we need those in a second. All right, so this is the training step, or this is one training step. And we need to pretty much do the same thing for the validation and test step, but we are going to fiddle with the numbers right here and what we are returning right here. So, oh, sorry, I have a typo here. So this will be validation step. And here I want to print the validation was. and I'm going to just return the loss. Yeah, this should do it. So this is the validation loss, and exactly the same thing with just minor adjustments we are going to do for the test step. Of course, you can extract this and make it look a bit nicer, but for us, this should do right now. So this is the test loss right here when we're doing the test step. So now that we have the training step, validation step, and test step, we are going to define the final method, which is a bit non-standard, I would say, and a bit specific to our example. And this will be the training epoch end method, in which we are going to compute the ROC score. So let's define it. And here I'm going to take these outputs of the training step. So this will have exactly this form. It will be a dictionary. And I'm going to take the labels and the predictions. And I'm going to iterate over all of the outputs. And those will be batched. So we will need to do to expand or flatten the results. And I want to detach and go to the CPU because we are going to do the training itself using CUDA or the GPU. And I'm going to append the labels. And I'm going to do the same thing for the predictions. All right, so now that we have the labels and the predictions, I'm going to convert those to torch tensors, which are going to be flattened. And I'm going to use torch.stack. All right, so now we have 2D tensors with the labels and the predictions. I'm going to compute the ROC score, or the area under the ROC, you might say. So to do that, I'm going to iterate over all label columns. So we're going to iterate and take the ROC score for each individual tag that we have in our labels. And to compute the score, I'm going to call the ROC, or area under ROC, and I'm going to show you where this is defined. Compute area under the receiver operating characteristic. This is into the PyTorch Lightning. And this even has source code if you're interested in. And I believe that, yeah, they have an example of how you can use it. It's very similar to what scikit-learn offers. All right, so this should work over the predictions at column or index for which label we are interested in right now. And I'm going to pass in the labels for this tag. And then I'm going to walk the result to TensorBoard. And this will be the name of the tag. And this will be for the training set only right now. So this will be the ROC score. And we are going to pass in the current epoch. Okay, so what this will do is going to evaluate the training set and tell us what is the ROC score for each individual tag. Last but not least, we need to define another method, which is going to be configure optimizers. And this will configure the optimizer as well as the warning rate scheduler. And this is where we will use all of the parameters for the warning rate scheduler that we've passed in to the constructor. First, I'm going to start with the optimizer. And this will be Adam with way decay fix. We're going to pass in the parameters of the model, pretty standard. And the warning rate is going to be this number right here. This is straight up taken from the fine-tuning recommendations done by the original BERT paper. Next, I'm going to calculate the warm-up steps that are required for the linear schedule or with warm-up. So this will be this number right here. And I'm going to use roughly 1/3 of the examples or the steps that we're going to do during an epoch for warm-up. So for 1/3 of the training for the current epochs, we are going to go from 0 to the warning rate. So this will be something like, let's say, something like here. And then from this point on, we are going to go back to 0 again. So I'm going to pass in the warm-up steps, which is going to be all of the steps that we're doing per epoch. And I'm going to divide this by 3. So this will be a 1/3. And the number of total steps that we're going to complete is going to be the steps per epoch. I'm going to multiply this by the number of epochs. So this won't be the 1/3. It's going to be much smaller number, I believe, because we are not multiplying by the number of epochs. But this should be fine in our example. And I'm going to take out the number of warm-up steps. And the scheduler is going to be the result of this. I'm going to pass in the warm-up steps and the total steps. So the syntax right here might be a bit funky. We need to return a list of optimizers and schedulers. In our case, those lists will be just containing the optimizer and the scheduler. So if we run through this, this should give us a complete model. It's quite a large number of wines, so the model is big. I know that's what she said, but yeah, this model is really big. And so let's create an instance of our model. Toxic comment tagger. The number of classes is going to be 6 because we have 6 tags. The number of steps per epochs is going to be the length of the training data frame, which is going to be divided by the batch size that we have. And if I do this, I need to pass in the last parameter, which is going to be the number of epochs, and this will be 10, a constant that we defined already. So if I instantiate this, this will go ahead and download BERT if it is not already downloaded. In our case, we did that. And I'm going to show you what an untrained model is going to return as a result. And here, what we need is something like this. We're going to take the sample item that we've passed in the previous video. And yeah. So this will get the input IDs and the attention mask and return loss and predictions. Note that we are not passing the labels here. and this should give the predictions for each possible tag. So note that we have a tensor with 6 values, and those will be primarily random at the moment because we haven't done any fine-tuning whatsoever. But this is going to change right now because we are going to train the model. And here comes the power of PyTorch Lightning. You basically don't have to do any more training loops. You have to just define the training, validation, and test steps, and most of the other stuff like iterating over the batches or the data loaders or taking care of what moving the data to some device or the model to some device to do the CUDA GPU or whatever you're training on. So to simplify all of this, they just define this trainer, which we are going to instantiate right now. And this takes a number of max epochs. So this will pass in the number of epochs that we have right here, the number of GPUs. We have only one GPU, and I'm going to specify how often the output of the training is going to be refreshed. So you need to pass in this because Google QA basically won't work as expected if it's lower than 20, I believe. So if we run this, it is saying you that we have one GPU available, even though it says that it is an array of 0, which is going to be the only GPU that we have, and it's going to use it because we set GPUs 1. Next, I'm going to start the training. So to do that, I'm going to call trainer.fit, and this accepts 2 parameters. The first is going to be the model, at least 2 parameters that we care about. And the next one is going to be the data module that is going to define how the data should be taken and used during training. So if we run this, we should hopefully see a summary of the model right here. And then the actual training will start. Of course, you can use many more helpers. Yeah, what we have here is quite good. You can use a lot more helpers. PyTorch Lightning allows you to specify, let's say, early stop callback. So let's say if you're monitoring the validation loss and it doesn't go lower for some time, you might stop the training. And you can do a lot of things using PyTorch Lightning, but I'm not going to focus on that in this video as much. If you want to see more about how to use PyTorch Lightning, let me know in the comments below. I might do a deeper dive into all possible callbacks and checkpoints and logging and basically TPUs, multiple GPUs. Of course, you can use multiple GPUs right here. It's so easy just to change this number if your machine contains multiple GPUs. And you can see that this is already training. You probably can't see all of it because I'm using a dark theme, but you can see that this is printing the loss, the validation loss, and the train loss. And I'm going to stop the training right here. And I'm going to show you the results of my pre-trained model, at least. All right. And let me show you what the TensorBoard is giving out. So you can load the extension TensorBoard, and you need to run the TensorBoard with using the training logs as a parameter. So the training starts and it creates this folder right here. In here, you have your first experiment, and you can change the name when you're defining the trainer. So in here, you'll find the TensorBoard events and the checkpoints, which are created for you by PyTorch Lightning. And this is pretty much an identical model that I've showed you how to do. And in here, you can see that I've trained this for 10 epochs. And this contains a lot of metrics, but most importantly, we have the ROC curves for each individual tag. And you can see that at the beginning, the ROC score was low, for example, for identity height, but during training, those numbers got better and better. Of course, you might want to train this model for longer. This might give you better results. So let's say for the insult, you can see again a huge spike in performance. All right. And the training was, you can see that it goes from a rather large value to something very, very reasonable. And the validation was something that we are more interested in, goes from 0.715 to 0.097, which is, I believe, is quite good. And you can observe the validation was right here. And you can see that the validation was quite low at the end of the training. And you can see that I'm using the trainer.save checkpoint to. So now that I've shown you how to train your model, I'm going to show you how you can use it to get some predictions. And to do that, I'm going to go ahead and download the pre-trained checkpoint. So this will go ahead and take the toxic comment classifier checkpoint from my Google Drive folder. I'm not sure that I'm going to keep this up because you can see that this is 1.3 gigabytes. So it's, again, a very large model. And I'm going to take an instance of that by calling toxic comment tagger load from checkpoint. And I'm going to pass in this checkpoint right here, which is now available here in our local files. Okay. And I got to specify the number of classes that we have. After this is instantiated, I'm going to call trained model.freeze, which will prepare our model for inference or faster inference. And after this is done, I'm going to start with a test comment. And let's say that we have something like this. I really hate you. So let's say that we have something very toxic like this. Next, we are going to use the tokenizer to encode the text, and I'm going to get back, take this, and pass in the test comment, and I'm going to change this to 128 and run through this. So this is now the encoded test comment. After that, I'm going to take the prediction from the trained model, and I'm going to pass in the input IDs and the attention mask here, and I'm going to look at the prediction. Okay, so you can see that there are numbers that are quite close to 1. So these are the tags which our model thinks most probably that should be added for this comment. And you can see that some of the other tags have very low probability. So one thing I'm going to do after this to do some post-processing is going to convert the test prediction to a NumPy array, and you'll see why in a second. I'm going to flatten this because you can see that we have tensor of tensors because this works with batches, of course. And I'm going to call NumPy on that. So this will be a float NumPy array right now with the same values right here. And next, I'm going to convert those values to the labels that we have for each tag. And I'm going to do that by iterating over the predicted probabilities and possible labels and applying a threshold for which we're going to take the labels. We are going to enumerate over all possible tags or labels. And I'm going to take the label probability. And if that probability is larger than some threshold, and this in our case is going to be 0.5, I'm going to say that the model thinks that this label should be applied to this text or this comment. So for our example, again, I really hate you, etc. Our model believes that the labels that should be applied are toxic, obscene, and insult, which is very good, I guess. So finally, I'm going to wrap all of it into a simple function that you can call called classify, which I've shown you at the start of the previous part. And I'm going to define this function. But this will take a bit more parameters that I've shown you in the beginning of the previous video. It's going to take the comment text, the model, the tokenizer, the label names, and some threshold for which we're going to specify 0.5 as a default. You might want to specify this a bit higher, but that's up to you and your business case, I guess. So I'm going to start by encoding this text right here. So after the encoding is complete, I'm going to get the prediction from the encoding. And I'm going to call that on the model that we're passing in this function. Next, I'm going to apply the same operation. We're going to flatten it and call the NumPy array from this. Next, I'm going to extract the predicted labels. I'm going to apply the threshold, which should be this parameter right here. And I'm going to look at the label names, which is another parameter. And I'm going to take the label probability from the prediction. This will give us the labels. And this will be basically the result of our function. So now that we have this, I'm going to try it out with a bit of examples, which we with an example that we start the series with. So let's say that we have this text. And I'm going to classify this with the trained model, the tokenizer, and the label columns. And I'm going to keep the threshold as it is. So if this runs, you can see that we have an error for which, let me check it. So I'm calling the model and it says that, yeah, I forgot to do enumerate here. Okay, so for this text, we have toxic, obscene, and insult, which is very good, I believe. And one interesting thing that you might want to try here is to pass in clean text or a text that doesn't contain any toxicity or bad words. And for this example, I'm going to use a phrase that I'm really happy. Like, let's say that it's from one of my favorite TV shows. I'm Meredith, and I'm good at supplier relations. So this is a text that is supposedly clean, it doesn't contain any toxicity, and I'm going to basically call the same function with the same parameters. And this should return an empty array. So there shouldn't be any toxicity. And you can see that this is the case. So I believe that this model has been fine-tuned very good, and you can try to fiddle with the parameters with the linear rate scheduler, and you can even go ahead and train it for more. You can try other BERT models or Albert or something completely different, I guess, and you might get even better results. But I'm continuously blown away by the performance of those BERT and transformer models in general for various NLP tasks. Of course, the power comes from the pre-trained, let's say, context in those. And I'm really glad that those models are open source, that the HuggingFace library transformers is available for free, and you can basically do some very cool stuff with that. So thanks guys for watching. I hope that you really enjoyed this series, and again I want to say thanks for hitting 5k subscribers. I'm going to create a notebook with all of it. With all of this, I'll be able to show you, I'll share the notebook with you into the description below, and I'm going to create a blog post which is going to detail everything that we've done so far. Of course, the blog post might contain even more or even better information. I'm going to reference all of the stuff that I've talked about right here. Thanks for watching. Please like, share, and subscribe. I'll see you next time. Bye bye.